What are the odds that the universe would line up this many strange events in the same narrow slice of time? In the span of just a few days, two distant stars suddenly brightened into naked eye visibility. Two powerful earthquakes ripped through Venezuelan bedrock, and an object from another star system wandered straight into the middle of an active solar storm. If you saw this as the opening montage of a science fiction film, you might roll your eyes and say, "Come on, that's too much. That would never happen in real life." And yet, it just did. Late September 2025 now sits in a category all its own, one of the most synchronized weeks of cosmic and terrestrial action ever recorded. Astronomers watched as twin nova eruptions flared to life in the southern skies. Seismologists tracked twin quakes in the same vulnerable region of Earth's crust, only hours apart. Space weather forecasters ran their models and realized that a billion-ton cloud of magnetized plasma from the Sun was crossing paths with 3I Atlas, only the third confirmed interstellar visitor in human history. Individually, each of these events has a perfectly ordinary scientific explanation. Together, they feel weird. That word matters here. Not apocalyptic, not mystical. Just weird in the most honest sense of the term. Unexpected, unlikely, and hard to ignore. The physics behind nova explosions, earthquakes, and solar storms has been studied for decades. None of these phenomena needs anything supernatural to occur. But timing is a different kind of problem. Timing is where human pattern recognition wakes up, leans forward, and whispers, "Are you sure this is just coincidence?" Tonight, we are going to slow that week down. We will stretch those few days out in front of you like a map and walk through them, step by step. We will visit the two stars that erupted into sudden visibility after thousands of years of quiet. We will stand, in imagination, on the shaking ground of northwestern Venezuela, as stress that has been building for decades finally gives way. We will follow the sun's outburst as it hurls a coronal mass ejection through the inner solar system. And we will watch 3I Atlas as it threads through that disturbed space, carrying ice and dust forged under an alien sun. Along the way, you will hear the clean, conservative answers from mainstream science. No proven link between space weather and earthquakes. No evidence that distant stellar eruptions influence our planet. No sign of intent or design behind 3I Atlas's arrival. You will also hear the questions that honest scientists still ask when the data cluster this tightly, and the possibilities they consider when old models are gently stretched by new observations. Most of all, this is an invitation, not to panic, but to pay attention, to let yourself feel that subtle unease when unrelated systems seem to move in rhythm, and then to calm that feeling with understanding. By the end of this journey, you will know exactly what happened during those strange days in September, what we can explain, what we cannot yet explain, and why this one interstellar visitor passing through a stormy corner of our solar system has captured so much of the world's imagination as space appears to collapse into chaos around it for now. To understand how this unusual week unfolded, it helps to lay the moments out gently, one by one, the way you might line up stones along the edge of a quiet trail. Nothing dramatic, nothing rushed. Just a simple sequence of events, each with its own place on the calendar, each carrying its own meaning. When viewed this way, the pattern begins to show itself, not as something mystical, but as something undeniably concentrated. A cluster of happenings that seem, at first glance, almost too well timed to belong to the same ordinary week. The story begins on September 23rd. In the pre-dawn hours of the southern hemisphere, a quiet star in Centaurus suddenly surged into visibility. V1935. Centauri, a system that had gone unremarked for generations, brightened enough for amateur observers using small backyard telescopes to confirm that a nova had erupted. News traveled quickly. Space-based observatories adjusted their pointing schedules. Data began to flow. One moment, the star had been anonymous. The next, it was a new source of high-energy light, its eruption recorded across gamma-ray and X-ray instruments. Barely 24 hours later, on September 24th, the focus of attention shifted from the sky to the earth beneath our feet. In northwestern Venezuela, an earthquake of magnitude 6.2 struck a vulnerable section of the crust. It was shallow, deceptively so, meaning that the shaking was intense and widely felt. Communities across the region reported buildings swaying, furniture rattling, and the subtle fear that comes with sensing something deep and ancient shifting underneath you. It was a fully natural event, explained by decades of pressure building along a complex network of faults, but it arrived with an unsettling sense of timing. The next day, September 25th, delivered a double development, as if the universe had decided that one nova and one quake were not quite enough. That morning, astronomers confirmed a second nova, V7994 Sagittarii, bright enough to catch the attention of observers across several continents. This kind of brightness, this quickly after the first nova, was statistically unusual. Not impossible, just rare. As the astronomical community absorbed that news, the ground in Venezuela shook again. A magnitude 6.3 event, deeper than the first, but packed with even more energy, rippled through the same general region. Residents who had just finished checking their homes for cracks found themselves stepping outside once more, looking toward the horizon and wondering how long the Earth planned to keep moving. Meanwhile, in the quieter upper layers of the Sun's atmosphere, a different sequence was beginning. Between September 26th and 29th, multiple coronal mass ejections launched from the Sun's surface, part of the natural surge of activity associated with the solar cycle's rising phase. Most of these ejections dispersed harmlessly into space, but one in particular caught the attention of space weather modelers. Its trajectory appeared to sweep directly across the region of space occupied by 3I Atlas, a visitor from beyond our solar system making a rare close passage through the inner planetary neighborhood. It was the kind of alignment that doesn't need exaggeration or drama. The simple chronology is compelling enough. A star flares, the ground shakes. Another star flares, the ground shakes again. Then the sun fires a billion-ton cloud of charged particles through the path of an object that was born near a different sun entirely. Each event explained on its own, each event familiar to science. Yet all of them pressed close together on the same calendar page, as though the cosmos were briefly running multiple plays in parallel. This is the power of sequence. When the mind sees several distinct systems, stellar, seismic, solar, interstellar, acting within hours of one another, it begins to ask whether the pieces matter more when placed side by side. That question is natural, it is human, and it is precisely why we slow everything down and look at the order, not just the events. Sequence creates its own kind of tension, a soft pull that makes you lean in and wonder what the next marker on the timeline will be. As Arthur C. Clarke once wrote, "Coincidence is what you have left over when you subtract the impossible." It is too early to subtract anything. Instead, we simply observe the accumulation. A nova, an earthquake, a second nova, a second earthquake, and then a blast of solar plasma aimed into the path of a traveling stranger from another star. Too many matches in too few days. Enough to make any careful observer pause, and enough to guide us to the next step in this story. Let's begin with the first spark, the moment a star erupted into sudden daylight. In the quiet hours before sunrise on September 23rd, an experienced skywatcher in Australia stepped outside to do what he has done for decades: scan the heavens for anything unusual. His name is John Seach, and among amateur astronomers, he is known for having a remarkable eye, one that notices the tiniest changes in the brightness of stars. On that morning, as he swept his camera across the constellation Centaurus, something caught his attention. A faint point of light that had never stood out before now appeared brighter than it had any right to be. He checked again, and again. The brightness was real. A nova had erupted. The star was V1935 Centauri, a white dwarf locked in a tight gravitational dance with a companion star. Most nights, it is too dim for human eyes, a quiet participant in the vast southern sky. But on that night, it brightened dramatically. Within hours, satellites orbiting above Earth confirmed what John Seach had seen from the ground. Space-borne detectors registered a spike in gamma rays, followed by flashes of X-ray light, a signature pattern of a nova eruption. A sudden, runaway burst of nuclear fusion had ignited on the surface of the white dwarf, sending light outward across thousands of years of space until it finally reached us in this small, present moment. Novae follow a reliable script in astronomy, but each one still feels like a small miracle. A white dwarf is the collapsed core of a once sun-like star, a body so dense that a teaspoon of its matter would outweigh a mountain. Its gravity is intense enough to pull material from a nearby companion. Gas slowly piles onto its surface, hydrogen mostly, layer after thin layer. When enough accumulates, pressure and temperature rise until the atoms can no longer resist. Fusion begins, not gently like in ordinary stars, but in a sudden wave that races across the surface. For a brief time, the star brightens by tens of thousands of times. It is not an explosion that destroys the star. It is a surface event, a brilliant flash from a dying remnant that still has the power to surprise us. V1935. Centauri displayed this entire sequence: a quiet star, a sudden brightening, a rush of high-energy radiation. For most years, that alone would have been the headline. A naked-eye nova is rare. Many astronomers go an entire lifetime without seeing one that wasn't assisted by a telescope or a camera. But this time, the sky had more to offer. Just a few days later, on September 25th, while the astronomical community was still analyzing data from the Centauri event, word came of another brightening, this time in Sagittarius. V7994. Sagittarius had undergone a similar eruption, bright enough for small telescopes and even dark sky observers to catch. Two novae, both reaching noticeable brightness, both within the same week. The last time the sky delivered a pairing like this at such brightness, many of today's observers were still children. The physics behind both events is the same: white dwarf, mass transfer, accumulation, thermonuclear runaway. Nothing in either eruption violated our scientific understanding. Nothing hinted at an exotic cause or an unknown mechanism. But novelty does not lie only in physics. It also lies in timing. Humans understand numbers, but we feel patterns. And seeing two stars flare into temporary brilliance so close together in time awakens that quiet question: are they connected? Science tells us the two systems are separated by immense distances, each governed by its own internal rhythms. There is no mechanism that ties them together. Yet the heart sometimes responds before the brain. Two sudden lights in the sky invite wonder. They invite the feeling, just the feeling, that the universe is clearing its throat to say something. This is where we keep the boundary clear. Facts remain facts. Feelings remain feelings. Both can exist without contradicting each other. You are allowed to marvel at the coincidence without leaping to conclusions. You are allowed to enjoy the rarity of two nova eruptions without imagining an invisible thread between them. That balance is part of what makes astronomy so rich. The sky gives you spectacle, and then it gives you understanding. And in this case, it gives you perspective as well. The photons that reached Earth in late September were not new. They had been traveling for centuries or millennia. When a nova brightens, it is not happening now in any human sense. It happened in the deep past. What you see is the echo of something long finished. You are looking at history in real time. Light that left its source before many of our ancestors had even begun mapping the stars. Light that crossed unimaginable distances to arrive in your field of view for a few brief nights before fading back into obscurity. A nova is a reminder that even dying stars can surprise us, said astrophysicist Sumner Starfield. And this week gave us two reminders back to back. Not because the laws of physics changed, not because the universe broke character, but because probability sometimes hands you a rare pairing. And in that pairing, you feel the strange thrill of seeing the familiar behave in uncommon ways. That feeling, that quiet sense of strangeness, is the beginning of the story we are telling tonight. But while the sky was flashing with ancient light, the earth beneath us began to move. When the earth decides to move, it does so without warning and without regard for whatever might be happening in the sky above it. Yet in this particular week, as two distant stars erupted into sudden brightness, something deep within our own planet shifted as well. The first tremor came on September 24th, only a day after the initial nova. It struck the northwestern region of Venezuela, a place where two tectonic plates meet in a slow and complicated struggle that has shaped the local landscape for millions of years. The earthquake registered at magnitude 6.2, but the number alone does not tell the full story. What mattered was its depth, less than 10 kilometers beneath the surface. That is extremely shallow, and shallow quakes tend to be far more forceful for those who live above them. Residents describe the shaking as abrupt and startling, the kind that makes you instinctively reach for a doorway or brace yourself against a wall. These are communities accustomed to minor tremors, but this one felt different. Its energy rose quickly through the crust, producing an intensity that rippled outward across cities and towns. For seismologists, the event was notable but not extraordinary. A shallow 6.2 in a tectonically active region is part of the natural rhythm of the Earth's shifting crust. And yet, tucked so close to the nova event of the day before, it added another point to the growing sense that this week was becoming unusually crowded. Then came the next morning. On September 25th, just as astronomers were confirming the second nova in Sagittarius, the ground in Venezuela moved again, this time with even more energy. A magnitude 6.3 earthquake struck the same broader region, deeper in the crust, but still powerful enough to be widely felt. People who had just finished checking their homes for damage found themselves back outside, listening to car alarms, watching power lines sway, and feeling the familiar unease that comes from sensing a part of nature that cannot be predicted. It was a second blow delivered to the same general area within hours of the first. This kind of pairing is not unheard of. Earthquakes often come in clusters because when one section of a fault releases its built-up stress, the force redistributes through the surrounding rock. Sometimes that redistribution triggers motion in a neighboring segment, setting off another quake. This is what seismologists call stress transfer, and it is one of the natural consequences of having a planet made of shifting plates and grinding boundaries. One movement changes the balance. The next movement restores it. And when the pressure settles again, the Earth rests for a while. In this case, the 6.2 likely adjusted the stress conditions in the region, helping set the stage for the 6.3 that followed. After that came a more modest 5.8 aftershock, a reminder that the crust rarely stops instantly, but instead gradually relaxes through a series of smaller movements. The pattern made perfect physical sense. Nothing in the data suggested an outside influence. Space weather does not trigger earthquakes. Solar storms, magnetic disturbances, and cosmic events operate on scales that do not meaningfully affect the dense mechanics of Earth's interior. And yet, even with that solid scientific grounding, the timing still stirred something in the imagination. 2 stars brighten above. 2 quakes strike below. Different realms, astronomical and geological, acting on their own terms, but appearing back to back in the same narrow window of time. It is natural to notice such pairing, natural to feel that subtle question rise. Why here? Why now? And why so close together? That is not superstition. It is simply the human tendency to look for rhythm in the world around us. Rhythm is how we make sense of complexity. It is a way of organizing experience, even when the underlying causes remain entirely separate. What matters in this story is not the idea of hidden connections. It is the simple fact that these events, unrelated as they may be, landed in sequence, a geological echo to the astronomical flashes overhead. You are not being asked to draw conclusions, only to observe the pacing of the week. The ground shook twice, just as the sky brightened twice. The Earth played its part in the pattern of the days, contributing its own pair of sudden movements to the growing list of September surprises. And understanding the physics behind these quakes does not diminish their emotional impact. It offers reassurance. You can recognize the strangeness of the timing without worrying that the world is behaving unpredictably. the tectonic plates continue their long, slow collisions. The stress continues to build and release according to principles that have guided our planet for ages. No cosmic trigger needed, no external influence required. Just Earth being Earth, steady, powerful, and occasionally reminding us that it is alive in its own way. 1 week, 2 bright stars, 2 strong quakes. Enough parallels to make anyone pause, even if the science behind them stays perfectly grounded. And as that second quake settled and the aftershocks faded, another part of the natural world was beginning to stir. This time, far above the surface, where our star was preparing a burst of its own. While the ground was shaking, the sun was preparing its own kind of eruption. High above the rumbling crust and far beyond the glow of erupting stars, another kind of force was building. Quietly at first, then with unmistakable intent. The sun, which spends most of its time in a state of gentle simmering, was entering a more restless phase. During solar maximum, its magnetic fields twist, tangle, and snap like overwound springs. And when one of those springs finally breaks, the sun releases something far more dramatic than light. It releases mass. A wave of charged particles and magnetic fields hurled into space at extraordinary speeds. This is a coronal mass ejection, or CME, and during the final days of September 2025, several of them were launched in quick succession. To understand what makes a CME so powerful, it helps to picture the sun's magnetic field as a series of loops rising above its surface. These loops are constantly shifting, stretching, and reconnecting, a process known as magnetic reconnection. When the field lines snap and link together again in a new arrangement, the energy stored inside them can erupt outward in a tremendous surge. The sun expels a massive cloud of plasma made of protons, electrons, and heavier ions, carrying with it a twisted magnetic structure that sweeps through the solar system like a storm front. Usually, these storms disperse harmlessly. They fan out across space, passing between planets or dissipating before reaching anything of interest. But not always. In 2007, a spacecraft called Stereo captured something remarkable, a CME colliding directly with the comet Enki. The impact was so forceful that it tore the comet's ion tail completely off, scattering it into space like strands of smoke in a gust of wind. Within hours, Enki formed a new tail, but the image of a comet being stripped bare in real time became one of the most striking demonstrations of how solar storms can reshape small bodies in the inner solar system. This history matters because of what modelers saw during the last days of September. As the sun fired a sequence of CMEs, analysts fed fresh data into Enlil, a computer model used to track how solar storms travel through space. One CME in particular caught attention. Its projected path placed it on a trajectory that would carry it straight through the region currently occupied by 3I Atlas, the interstellar object that had entered our solar system earlier in the summer. For the first time since humans discovered visitors from beyond our star, one of them might be brushing directly through the wake of a solar storm. It is important to emphasize that this was not a collision in the traditional sense. Space is vast, and CMEs are diffuse. But the idea of an object from another star system drifting through the magnetic debris of our own sun evokes an image so striking that it pauses the mind. Atlas was passing just inside the orbit of Mars at the time, positioned in a way that made it especially vulnerable to changes in the solar wind. And because solar maximum amplifies every kind of solar activity, the environment around it was more turbulent than usual. What makes this moment so unusual is not danger. It is rarity. Most comets in our solar system have experienced similar encounters dozens, even hundreds of times. But 3I My Atlas is different. Its chemistry was forged elsewhere. Its dust grains, ices, and trapped gases carry the fingerprints of a distant star system, shaped by conditions we can only imagine. When sunlight hits it, we are not just observing a comet. We are observing alien material reacting to our star for the first time. Add a CME into that mix, and suddenly the situation becomes even more intriguing. If the CME did brush past Atlas, several things could have happened. The coma, the bright cloud of gas surrounding the nucleus, might have expanded or brightened briefly as the incoming particles energized the molecules near the surface. The ion tail could have twisted, kinked, or momentarily broken, much as Encke's tail once did. Changes in its spectral signature could reveal subtle shifts in the gases being released from the surface, offering rare clues about the composition of matter that once orbited a different sun entirely. None of these effects would be dramatic to the naked eye, but in the world of astrophysics, even slight deviations can tell profound stories, and that is where the sense of wonder enters. A visitor from another star, touched, however gently, by a storm from ours. Not fiction, not imagination, just physics unfolding in a way that feels almost poetic. The solar system is usually quiet enough that such alignments pass unnoticed. Yet here, in the space of a single week, already filled with nova eruptions and shifting ground, the sun added its own chapter, sending a pulse of energy across millions of miles that may have intersected perfectly with the path of an interstellar traveler. When Carl Sagan once wrote, "Comets remember places we will never see," he captured the idea that these icy wanderers are time capsules. They carry memory, they carry history, and in moments like this, they carry the story of how their foreign past meets our present. What happened in late September was not dramatic, not dangerous, and not beyond the laws of nature, but it was rare. Rare enough to stand out even in a universe full of motion. Rare enough to earn the title of something truly weird. But to understand how weird this really is, we need to explore the science beneath each layer. When several unusual events line up in a tight bundle of days, the mind does something automatic and deeply human. It begins to search for patterns. This instinct is older than science, older than writing, older than history itself. It comes from a time when noticing the rustle of grass or the flicker of movement at the edge of firelight meant the difference between safety and danger. The brain learned to connect dots quickly, sometimes too quickly, because missing a connection was riskier than imagining one that wasn't really there. That ancient wiring still lives in us. And during weeks like the one we have been exploring, it wakes up. You might feel it already. The subtle sense that nova eruptions, earthquakes, solar storms, and the arrival of an interstellar traveler happen too close together to be dismissed as simple coincidence. You wouldn't be alone in feeling that. Even seasoned astronomers, grounded firmly in data and experience, admit that certain stretches of time carry an almost uncanny rhythm. A rhythm that makes unrelated events seem as though they are part of a shared melody. We know, rationally, that the sky and the earth and the magnetic storms of the sun answer only to their own internal rules. But emotion works on a different clock. Synchronicity is the word often used for moments like this. Not causation, not connection, just the appearance of meaning. The sensation that events across vast distances, governed by separate forces, have somehow begun to move in parallel. Think of it as a kind of psychological echo chamber. When one striking event occurs, the next one lands a little louder in memory. A third feels louder still. Soon, the mind perceives a shape where, statistically, there may be none. Not because the universe is sending signals, but because our brains were built to interpret sequences, to cluster events together, to create story out of scattered moments. This week offers a perfect example. A nova brightens into sudden daylight. A quake shakes the crust beneath a distant coastline. Another nova glows to life. Another quake follows. The sun releases a wave of solar plasma, and an interstellar object happens to be drifting through the space it crosses. Each event is solitary, driven by its own mechanics. The fusion runaway on a white dwarf surface has no relationship to the grinding motion of tectonic plates. The shifting of Earth's crust does not influence the tangled magnetic fields of the sun. A coronal mass ejection cares nothing for where a comet, interstellar or not, happens to be drifting. And yet, when the entire sequence plays out in less than a week, it is hard not to feel the faint suggestion of a hidden thread. A suggestion that something coordinated is happening behind the scenes. The rational mind steps in and reminds us that the universe is vast and busy, that rare things occur more often than we expect when we observe a large enough canvas. But the emotional mind lingers on the thought that maybe, just maybe, these events are part of something larger, something choreographed, something intentional. This is where calm reflection becomes important. The world is full of patterns, but not all patterns are real. The human tendency to see shapes in cloud formations, to find faces on distant planets, or to imagine stories in star alignments comes from the same psychological architecture that interprets event clustering as meaningful. We are storytellers by nature. We connect fragments into narratives. And when nature presents us with an unusual cluster, we respond with narrative instinct, long before we respond with analysis. Science offers clarity here. It tells us that the nova eruptions came from white dwarfs, following cycles that had been building for centuries or millennia. The earthquakes resulted from stress accumulated in the Venezuelan crust along a fault system that has shifted for ages. The CME was one of many storms released during the sun's active phase, and 3I Atlas arrived not because it was drawn here, but because it has spent countless millennia drifting through interstellar space on a path that happened to intersect our own. Independent mechanisms, independent histories, independent causes. But feelings don't vanish simply because facts are known. Instead, they soften, they settle. They open a space where wonder can exist alongside understanding. Moments like this remind us that the universe does not need intention to inspire awe. Coincidence alone can do that. a series of unrelated events brought close together in time, can create something that feels almost gently theatrical, something that invites attention, something that makes the world feel momentarily more mysterious without stepping outside the boundaries of physics. Meaning, in this sense, is not something hidden in the universe. It is something the human mind paints onto the universe, a quiet overlay, thin and personal, that gives shape to the chaos and beauty of everyday cosmic motion. That paint is not false. It is simply ours, a natural response to a world that is far larger, far older, and far more active than we can ever fully witness. And so we pause here, not to draw conclusions, but to acknowledge the space between emotion and explanation, to recognize that the weirdness we feel is real, even if the mechanisms behind it remain fully independent, to enjoy the quiet tension of a week that seemed to echo with meaning, even as science tells us otherwise. So let's look deeper, starting with the stars themselves. When we talk about nova eruptions, it helps to slow everything down and step back into the quiet architecture of a dying star. Not the dramatic end that turns a sun into a supernova, but a gentler, more cyclical process, one that unfolds over centuries or millennia, and then announces itself with a sudden flash we briefly see from Earth. The nova that observers witnessed in late September did not mark the death of a star. It marked a moment within a long, repeating story, one that astronomers have been deciphering for more than a century. And understanding that story transforms strangeness into familiarity, giving shape and rhythm to something that at first glance seems impossible. At the heart of every nova lies a white dwarf, the dense, compact remnant of a sun-like star that has exhausted its fuel. The structure of a white dwarf defies everyday intuition. Imagine a sphere roughly the size of Earth, but containing half the mass of the Sun. The matter inside it is packed so tightly that atoms are crushed into a state known as electron-degenerate matter. A teaspoon of this material would outweigh mountains. Gravity on its surface is hundreds of thousands of times stronger than anything we can experience. It is an object defined by stillness and pressure, a stellar ember that no longer burns but holds onto astonishing thermal memory. White dwarfs do not shine from fusion. They shine because they are slowly cooling leftovers. But when a white dwarf exists in a binary system, when it orbits another star, its quiet life can change. If the companion star expands or sheds its outer layers, the white dwarf's gravity can siphon material from it. Hydrogen, the universe's simplest and most abundant element, begins to collect on the dwarf's surface. This process unfolds at an unhurried pace, atom by atom, puff by puff of drifting gas. It can take thousands of years to accumulate enough material for the next stage, and during all that time, the white dwarf sits in silence, gathering a thin shell of fuel. Eventually, the hydrogen layer becomes dense enough and hot enough to ignite. But because the surface gravity is so immense, that ignition is not a gentle spark. It is a runaway reaction. Fusion spreads in a wave across the surface, releasing energy far faster than the star can radiate it. For a few hours or days, the white dwarf brightens dramatically. It becomes tens of thousands of times more luminous than it was moments before. To us, this looks like a sudden appearance. A star that was invisible becoming visible overnight. But in truth, it is simply the surface offering a brief flare of stored potential before settling back into its long cooling cycle. The nova does not destroy the white dwarf. It clears away the accumulated hydrogen in a flash, returning the star to a quieter state. Over time, the process begins again. Accumulation, ignition, eruption, rest. Each cycle can take centuries or longer, and because these stars are so far away, we may witness only 1 or 2 eruptions in the entire lifetime of human observation. That rarity makes each nova feel special, even though the physics behind it is well understood. What made the V1935 Centauri and V7994 Sagittarius events especially intriguing was not that they happened, but that they happened so close together in visibility and in time. Both produce characteristic high-energy signatures. When a nova erupts, it sends out not only visible light, but also gamma rays and X-rays, forms of radiation that travel effortlessly through space. Earth's atmosphere shields us from these wavelengths, but orbiting satellites can detect them with exquisite sensitivity. Within hours of the first nova's discovery, instruments aboard space telescopes lit up with readings. They recorded the emission spikes that matched theoretical predictions, a burst of gamma rays followed by a softer afterglow of X-rays. When the second nova erupted just days later, the pattern repeated itself. This kind of high-energy confirmation is invaluable because it helps astrophysicists refine their models. It tells them how much material accumulated on the white dwarf's surface, how quickly the fusion wave spread, and how efficiently the star ejected the outer layers it had gathered over so many centuries. Every nova, even a textbook example, adds a new data point. And because human observers have only been monitoring the sky systematically for a little more than a century, many of these data points come from unexpected and delightful collaborations between professional observatories and amateur skywatchers. Amateur astronomers play a unique role in nova detection. They scan the sky night after night, not with the intention of making headlines, but out of quiet dedication and curiosity. They notice when something looks a little brighter than it should. They compare photographs, pixel by pixel. They submit alerts that later turn into global observations. In a very real sense, nova studies depend on this partnership. The first eyes to catch these eruptions are often not those of space agencies or giant observatories, but those of individuals standing alone under dark skies, guided by experience and intuition. One of the most captivating aspects of nova light is the time it takes to reach us. When you look at a brightening star, you are witnessing a moment that happened long before your grandparents were born. Light from V1935 Centauri and V7994 Sagittarius left their origins thousands of years ago. It traveled through interstellar space unimpeded, carrying with it a message from a distant past. By the time it arrived in late September 2025, the eruption itself was ancient history. This delay does not make the moment less meaningful. If anything, it adds depth. You are seeing the afterglow of a long finished event. You are witnessing the universe's memory at work. Dr. Edward Sion once wrote, "A nova is a whisper from a dying star telling you it's still alive." In that whisper, we hear both the fragility and resilience of stellar remnants. We hear the echoes of cycles far longer than human lifetimes. And when two such whispers reach us within days of each other, it is natural to pause, to marvel, and to feel that subtle sense of cosmic choreography, even if we know, scientifically, that the two stars share nothing more than the coincidence of timing. And just as stars have their cycles, so does the earth beneath us. To understand why the earthquakes in Venezuela fit cleanly within the physics of our planet, even if their timing felt uncanny, we need to settle into the slow, deliberate mechanics of Earth itself. Unlike the sudden flare of a nova or the sweeping arc of a solar storm, earthquakes belong to a world of pressure, friction, and the silent grinding of rock against rock. Their story is written not in light, but in strain. And when we read that story carefully, what looks like coincidence becomes something far more familiar. A planet following the same rules it has obeyed for millions of years. Northwestern Venezuela lies in a complex tectonic zone shaped by the interaction of the Caribbean Plate and the South American Plate. These two enormous slabs of lithosphere push, drag, and scrape past each other along a boundary that geologists classify as a strike-slip fault system, similar in some ways to California's San Andreas Fault. But here, the motion is slower, the angles more irregular, and the stresses more unevenly distributed. Sections of the boundary can remain locked for years, storing strain the way a bent branch holds tension long after you release your grip. Eventually, the rock reaches a point where it can no longer resist the pressure. It slips. And when it slips, the energy that had been building for decades is released in seconds. The earthquake on September 24th, the M6.2 event, occurred at a very shallow depth. Shallow quakes are uniquely forceful because the energy has little crust to travel through. It reaches the surface quickly, hitting communities with a strong jolt that feels abrupt and startling. There is no pause, no gradual ramp, just an immediate translation of stress into motion. That is why people across the region describe the shaking as sudden, sharp, and briefly disorienting. It was not an especially large earthquake by global standards, but shallow events often feel larger than their magnitude suggests. When the crust adjusts in one spot, the surrounding region feels the change. Stress that was once distributed along a wider section of the fault becomes concentrated in new places. This redistribution can trigger a second quake, especially if a nearby segment of the fault was already close to its own breaking point. That is what seismologists call stress transfer, an interaction not of cosmic forces, but of rock, friction, and geometry. The M6.3 earthquake on September 25th fits this pattern precisely. Slightly deeper, slightly more energetic, it ruptured a neighboring part of the fault system that had been brought closer to failure by the previous day's event. After the pair of strong quakes, smaller movements followed. A magnitude 5.8 aftershock rippled through the region, a natural echo of the prior ruptures. Aftershocks almost always follow a predictable decay curve known as Omori's Law. Many occur shortly after the main shock, then fewer as time passes, tapering steadily until the crust settles again. This sequence, main shock, second shock, aftershocks, is so common that seismologists can model the expected number and intensity of future tremors with remarkable accuracy. It is the geological equivalent of watching ripples spread across a pond after a stone is thrown. What these quakes do not correlate with is space weather. Solar flares, coronal mass ejections, and geomagnetic disturbances all operate within the Sun's outer atmosphere and the magnetic environment surrounding Earth. They influence satellites, power grids, radio transmissions, and auroral displays. But they do not meaningfully affect the slow, dense mechanics of tectonic plates, kilometers beneath the surface. The forces involved are simply too different in scale and medium. Earthquakes are driven by internal planetary heat, mantle convection, and the long-term shifting of crustal blocks. Nothing in solar activity changes the friction along a fault line or the pressure within a locked segment of rock. Understanding this brings stability to the story. It reminds us that even in a week filled with rare astronomical events and shifting geomagnetic conditions, Earth was still following its familiar rules. The timing of the quakes may have made them feel connected to the nova eruptions overhead, but the mechanisms behind them remain grounded, autonomous, and predictable in their own way. They were part of a natural cycle, not signs of instability, not consequences of cosmic disturbances, and not evidence of any influence from beyond the planet, just the crust-releasing strain it had carried for far longer than any of the week's celestial events had been unfolding. This contrast between the predictability of tectonic processes and the randomness of when we happen to notice them creates its own kind of fascination. Earthquakes occur on human timescales, sudden and visceral. Novae occur on stellar timescales, ancient and serene. Yet when their moments of visibility overlap, our minds instinctively try to connect them. We sense rhythm where there is none. We feel coincidence as intention, simply because it arrives wrapped in the same few calendar days. Still, even knowing that the two phenomena operate on separate clocks does not remove the quiet wonder of the overlap. It simply places it in context. Earth moved because Earth was ready to move. The stars brightened because their stored fuel was ready to ignite. The human mind, witnessing both in a single sweep of days, paints meaning between them. And that meaning, however personal, however symbolic, does not change the underlying stability of the planet we stand on. But while Earth followed its ancient rhythms, the sun was reaching a fever pitch. To understand why late September felt so turbulent, not just on Earth, but across the entire inner solar system, we need to widen the frame and look at the larger environment our planet and 3i Atlas were moving through. The sun, usually a predictable beacon of warmth and light, was entering one of its most restless phases. Solar cycle 25 had reached its peak, and when the sun reaches peak activity, the space around it becomes louder, denser, and far more energetic than usual. Every 11 years or so, the sun's magnetic field flips. This reversal marks the transition from a quiet solar minimum to a highly active solar maximum. During the maximum, the sun's surface becomes mottled with sunspots, regions of twisted magnetic tension. These spots are not blemishes. They are reservoirs of stored energy, ready to erupt. As the magnetic field becomes more tangled, the frequency of solar flares increases. The flux of high-energy particles rises. CMEs launch more often and with greater force. What was once a smooth solar wind becomes a pulsing, variable tide that surges through interplanetary space. In September 2025, that tide was near its strongest. Solar cycle 25 had exceeded early predictions. producing more sunspots than expected and unleashing flares at a surprisingly rapid pace. Each flare released bursts of radiation across the electromagnetic spectrum, from ultraviolet waves to X-rays. Each CME sent massive clouds of charged particles sweeping outward, their trajectories tracked by satellites and space weather centers around the world. This was not an unusual solar maximum, but it was an energetic one, and its effects could be felt far beyond the realm of astronomy. Space weather forecasters often describe solar maximum as a kind of celestial turbulence. The sun's magnetic field becomes unstable. The heliospheric current sheet, a giant undulating surface that stretches across the solar system, warps and twists. This warping modulates the particles streaming outward from the sun, affecting everything from spacecraft communications to the glow of the auroras. And in certain seasons, particularly around the equinoxes, another phenomenon amplifies geomagnetic response, the Russell-McFerrin effect. This effect occurs because of the geometric alignment between Earth's tilt and the direction of the solar wind during equinox months. When the angles line up just right, Earth's magnetic field becomes more efficient at absorbing solar wind energy. Even a moderate CME can trigger stronger geomagnetic storms than it would at other times of the year. In late September, conditions were ideal for this amplification. Not only was the sun firing multiple CMEs, but Earth's magnetic orientation made it easier for those incoming waves to couple with the planet's magnetosphere. The result? Heightened auroral displays, satellite precautions, and a general sense that the space environment was noisier than normal. The effects were not merely theoretical. Communication systems became more sensitive. Power grid operators entered a phase of increased alertness. Airlines adjusted some high-latitude flight paths to minimize radiation exposure. GPS accuracy fluctuated. These were the ordinary, manageable impacts of solar maximum. But combined with the timing of nova eruptions and regional earthquakes, they contributed to the feeling that the cosmos had turned up both its volume and tempo. Scientists who study the sun often describe this phase with awe rather than alarm. Dr. Lisa Upton once remarked, "Solar maximum is the sun's heartbeat accelerating. It is not a crisis, it is a cycle, a rhythm baked into the physics of our star, repeating across centuries." Each maximum reminds us that the sun is not a static lamp in the sky, but a dynamic, breathing furnace whose moods ripple across billions of miles. This turbulent backdrop matters deeply because of who, or rather, what, was traveling through it. 3I Atlas, the interstellar visitor carrying dust and ices from a long-dead star system, was drifting through a region of space made more chaotic by the sun's heightened activity. Every particle, every magnetic disturbance, every wave of energized plasma created an environment unlike the one Atlas had experienced in its vast journey across interstellar darkness. Solar maximum sets the stage. It is the canvas on which the week's events were painted. It explains why CMEs were plentiful, why the solar wind was variable, and why any object passing through the inner solar system in late September would encounter a far livelier environment than usual. And it is within this heightened state, this majestic turbulence, that our story turns back to the object at the center of the week's greatest mystery. And in the middle of that storm, something from another star was passing through. before the last week of September became crowded with nova eruptions, earthquakes, and solar storms, something else had already entered the frame of the solar system. A quiet traveler from far beyond our sun's domain. Its arrival had gone largely unnoticed at first, detected only by careful sky surveys and the algorithms that sift through thousands of nightly observations. But as September unfolded, that traveler moved closer, threading its way into a solar environment that had grown unusually restless. Its name was 3I Atlas, only the third confirmed interstellar object ever observed by humanity, and it was about to pass through the most chaotic moment in solar cycle 25. The discovery itself came earlier in the year. Automated scanning programs run by the Asteroid Terrestrial Impact Last Alert System, better known as ATLAS, captured the faint trace of a moving object whose trajectory didn't fit the usual pattern of comets from our own Oort cloud. Its orbit was hyperbolic, meaning it was not bound to the sun. Instead of looping gently around our star, it was following a one-time, open-ended curve that would carry it in, around, and out again, forever. That shape alone told astronomers everything they needed to know. This visitor did not originate here. It came from the space between stars, carrying material older than the planets and untouched by the sun until now. Interstellar objects travel differently from the comets we are used to. Their speeds are higher, their angles steeper, and their composition can be markedly different. They have spent millions, perhaps billions, of years drifting through the quiet vacuum between stars where nothing warms them, nothing pulls them, and nothing disturbs their long sleep. When one of these objects finally wanders close enough to a star, the change is profound. Radiation begins to heat its frozen surface. Ices that were locked solid since before Earth existed begin to sublimate. A coma forms, a diffuse, shimmering envelope of gas and dust, and the object takes on the appearance of a classic comet, not because it behaves like those we know, but because the laws of physics treat foreign material the same as familiar material under enough heat. 3I Atlas began to brighten in late summer as it crossed the outer regions of the inner solar system. Telescopes trained on it from Earth recorded a coma far larger than expected for an object of its size, suggesting that its ices were particularly volatile or structurally fragile. But what made the approach especially compelling was its trajectory relative to Mars. In early October, Atlas would pass near the orbit of the red planet, offering NASA, ESA, and especially China's Tianwen-1 spacecraft a rare observational window. Few interstellar objects have ever come this close to a planet. Fewer still have done so while the sun was approaching the crest of its most active phase. The timing was remarkable. Atlas was on approach just as the sun was firing multiple CMEs, and just as the solar wind was becoming more irregular and energized. Most comets approaching perihelion, its closest point to the sun, experience some disturbance from the solar wind, but Atlas was entering a far less predictable environment. A CME passing through its path could compress its ion tail, distort its magnetic interaction, or momentarily increase its brightness. These changes would not be dangerous. They would be diagnostic. They would help scientists learn about the composition of interstellar material by watching how it responded to a sudden wave of charged particles. Perihelion, The point where Atlas would swing closest to the sun was approaching in November. But even in late September, astronomers were preparing for the moment. Observation schedules were adjusted. Instruments were recalibrated. Specialized filters were ready to capture any shifts in emission lines that might signal chemical changes. The window was brief. Interstellar visitors travel fast. By the time most people on Earth even learned that Atlas existed, it had already covered millions of miles and was accelerating toward the point where solar heat would reshape its coma, its tail, and its visible signature. The weirdness of its timing did not lie in its physics. The orbital path of Atlas had been calculable since the moment of discovery. There was nothing unnatural about its arrival during autumn of 2025. What felt strange, what gave the week its uncanny flavor, was that an object from another star system was passing through the inner solar system at the exact moment when the sun was hurling some of the most active space weather of the cycle. If Atlas had arrived a year earlier or a year later, the environment around it would have been quieter, calmer, more predictable. But instead, it arrived now, threading its way through a space charged with magnetic storms and illuminated by the afterglow of nova light arriving from stars far beyond our reach. As it neared Mars, scientists used every tool available to measure its behavior. Radar reflections were too faint to provide structure, but optical imaging revealed subtle asymmetries in the coma. Spectral readings hinted at a mix of gases uncommon in typical Oort cloud comets. Possibly higher carbon monoxide content, possibly different dust-to-ice ratios. Each measurement added detail to the story, pieces of a puzzle that would be assembled long after Atlas had left our skies. But the most striking element remained the same. An interstellar traveler was moving through the sun's most turbulent moment, right as the solar wind grew heavier, right as CMEs swept across the inner system, and right as humans were preparing for one of their best ever opportunities to study such an object. Scientists often talk about observational luck, the chance alignment of timing and technology that makes certain discoveries possible. Atlas became one of those cases. A visitor from another star arriving during the sun's most chaotic moment created a natural experiment that no one could have planned. If the CME brushed past it, changes in its brightness or tail structure could provide clues about the strength of its nucleus, the character of its ices, and the way materials formed under a foreign sun react to energetic disturbances. Even if nothing dramatic happened, the mere possibility of interaction made the approach feel significant, as though the cosmos were offering an experiment in real time. This sense of quiet wonder threads through the entire story. Atlas was not dangerous. It was not unpredictable. It was simply rare, an emissary from a star that no longer shines, passing through the restless breath of our own star for the first and last time. It reminded observers that the solar system is not isolated, that sometimes material from other corners of the galaxy drifts close enough for us to glimpse its secrets before it disappears again into the darkness. And as if the sky wasn't busy enough, another comet stepped onto the stage. As if one interstellar traveler and a restless sun were not enough to fill the week with a sense of cosmic theater, another actor quietly entered the stage. Comet Swan. Unlike 3i Atlas, Swan is not an object from beyond the stars. nor is it part of any grand astrophysical mystery. But its arrival in late October, glowing gently against the backdrop of an already crowded sky, added a final layer of atmosphere to a story already rich with motion, timing, and celestial coincidence. Comet Swan takes its name from the solar wind anisotropies camera aboard the SOHO spacecraft. The instrument is designed to track variations in the solar wind by noticing faint hydrogen emissions. But over the years, it has also become an unlikely discoverer of comets. These comets often appear first as diffuse bright patches in SWAN's ultraviolet images before ground-based telescopes ever detect them. This was the case in 2025, when observers noticed a soft, expanding glow that did not match any known object. Within days, telescopes on Earth confirmed its presence, a small comet brightening faster than expected as it approached the inner solar system. SWAN was no rival to the brightness of major comets like Hale-Bopp or Neowise, but it carried a charm of its own. It brightened just enough to attract attention from amateur observers, especially those using binoculars under dark skies. As October progressed, its coma grew larger, reflecting sunlight with a soft, bluish tint caused by carbon-based gases fluorescing in solar radiation. These subtle changes made it a favorite among astrophotographers who captured its delicate arc across star fields as though it were a brushstroke added to the sky's unfolding painting. What made SWAN's appearance even more striking was its timing relative to lunar and meteor cycles. When the new moon arrived, it left the sky darker than usual, creating ideal viewing conditions for faint objects. At nearly the same time, the Orionid meteor shower began to intensify, sending streaks of light across the eastern horizon before dawn. A quiet comet, a moonless sky, and a river of meteors all arriving together formed a natural stage, one that made the late October sky feel unusually alive. Observers who stepped outside before sunrise found themselves watching 3 layers of motion at once. In the background, the Orionids, tiny fragments of Halley's Comet burning up in Earth's atmosphere. In the midground, Comet Swan, drifting with unhurried grace. And in the deeper distance, the faint, faraway movement of 3i Atlas, still brightening slowly as it arced toward its November perihelion. None of these objects were connected physically, but their simultaneous presence created a mood that was difficult to ignore. The sky looked crowded, as though the universe were staging a quiet performance for anyone patient enough to look up. SWAN also offered a point of comparison, helping to highlight just how unusual 3i Atlas really was. SWAN behaved like a normal comet, predictable, bounded to the sun, shaped by familiar forces. Its brightening followed the standard curve as solar heat caused its ices to sublimate. Its tail flowed smoothly with the solar wind. Its chemistry matched that of comets that have visited the inner solar system many times before. In contrast, Atlas carried with it the fingerprints of a different birthplace. Its coma behaved unpredictably. Its composition hinted at unfamiliar ratios of gas and dust. Even its brightness fluctuations suggested materials that were reacting differently to solar radiation. Seeing SWAN and Atlas in the same season offered a kind of natural control experiment. One comet behaving exactly as the models predict. Another with a hyperbolic orbit and alien chemistry, moving through the same environment but responding in subtler, more enigmatic ways. For astronomers, This contrast was a gift. For casual observers, it was a reminder that the sky holds more variety than we often imagine. And for anyone paying attention to the sequence of events unfolding across late September and October, it added yet another piece to a week, now a month, that felt unusually rich with cosmic motion. Comet Swan did not bring danger, and it did not carry secrets from other stars. But it completed the tableau, a comet glowing softly in the darkness, a meteor shower sweeping across the sky, and an interstellar traveler approaching its moment of closest approach. Together, they created a sense of layered wonder, like overlapping melodies in a quiet cosmic symphony. Now, let's put the entire cosmic puzzle back together. When you lay each event of late September and October side by side, something soft but unmistakable emerges. A rhythm, a cadence, a flow. None of the events share a physical cause. None depend on the others. And yet, when placed on the same timeline, they form a pattern so concentrated that it becomes impossible not to pause and simply take it in. This is where the week earns its title. Not supernatural, not alarming, but undeniably, quietly, weird. It begins with light. On September 23rd, V1935 Centauri erupts into a brilliant nova, sending photons that began their journey centuries ago, finally sweeping past Earth. A day later, while astronomers are still adjusting exposure times and recalibrating sensors, the crust beneath Venezuela shakes with a magnitude 6.2 earthquake, a shallow, abrupt jolt that feels entirely terrestrial, but lands with uncanny proximity on the timeline. Within hours, the sequence builds. On September 25th, another nova flares into visibility, this time from the direction of Sagittarius. The same day, the Venezuelan crust releases a second burst of energy, a 6.3 quake triggered by the stress transfer of the first, 2 brightening stars, 2 shifting fault lines, all within 48 hours. By now, the sky and the earth seem to be taking turns, each offering its own dramatic pulse. And then the sun steps forward. Between September 26th and 29th, multiple CMEs erupt from the solar surface, propelled by the heightened activity of Solar Cycle 25's peak. Most of these storms sweep harmlessly through space, but one, just one, has a modeled trajectory that passes directly across the orbital path of 3I Atlas. A visitor from another star drifting into the wake of our own star's magnetic turbulence. A convergence no storyteller would dare script too obviously, yet one that unfolds naturally in the real sky above us. This alone would make the week feel unusual, but nature wasn't finished. In early October, as the solar wind continued pulsing with increased density and variability, Atlas brightened further while moving toward a close pass near Mars. Tianwen-1, the Chinese spacecraft orbiting the planet, prepared for a rare opportunity to photograph an interstellar object up close, a moment made even more significant by the surrounding geomagnetic turbulence. A hyperbolic traveler, sculpted in another system, entering the most chaotic moment of our sun's current cycle. Not dangerous, not impossible, just rare. And while all this unfolded, another comet, Swan, made its gentle entrance. It brightened under a moonless sky, drifted among the Orionids, and added one more brushstroke to an already crowded cosmic canvas. Nothing dramatic, nothing threatening, but its timing added volume to the sense that the sky had become unusually busy. as though multiple stories were converging for a brief, delicate overlap. Placed in this order: nova, earthquake, nova, earthquake, CME, atlas, swan. The sequence begins to resemble choreography. Not in the literal, causal sense. Science makes that boundary clear. The white dwarfs that ignited into nova had been preparing for centuries. The tectonic plates beneath Venezuela had been straining for decades. The sun's rising activity belongs to an 11-year magnetic cycle. Atlas has been drifting through interstellar darkness for longer than humans have existed. And Swan simply moved along the ordinary arc of a periodic comet. But human perception works differently. We're pattern seekers, narrative builders. When events cluster close together, we hear harmony even if the instruments are playing separate songs. We sense arrangement where there is only coincidence because our minds evolved to treat sequence as meaning. Even knowing the science, the feeling remains. A quiet internal whisper that says, "This is all happening too close together." And maybe that is the real essence of weirdness. Not the breaking of physical rules, but the alignment of unrelated events in a way that feels momentarily coordinated. Like a set of dominoes spaced just far enough apart that each falls for its own reason, yet from our vantage point appears as a single motion. This was a rare week where the universe felt coordinated, not in purpose, not in message, but in timing. And timing, more than anything else, shapes the way we experience the world. It shapes wonder. It shapes attention. It shapes the stories we tell about the sky and our place beneath it. And so, as the noise fades, let's settle into the quiet that remains. Now that the timeline has unfolded and each event has found its place, something softer settles in. The week was crowded, yes. The sky was bright. The earth was restless. The sun was alive with magnetic fire. But beneath all of it lies a deeper truth, one that brings the mind gently back to equilibrium. The universe is chaotic in the way oceans are chaotic, full of motion, full of cycles, full of energy. But it is also indifferent. It does not lean toward meaning or away from it. It simply exists, vast and steady, moving according to laws that have shaped its history long before we were here to witness even a fraction of it. The nova eruptions were not messages. The earthquakes were not warnings. The CMEs were not aimed. Atlas did not arrive on purpose. They were simply events unfolding across different scales of space and time that briefly overlapped in our field of view. The patterns we saw, those soft, tempting shapes that seemed to stretch across the calendar, were patterns created by us, not imagined in a false way, but painted gently onto the canvas of the week by a mind designed to seek rhythm. That instinct is part of what makes us human. It allows us to tell stories, to recognize beauty, to find meaning even in coincidence. Wonder is not a flaw in perception. It is a feature, a way of connecting ourselves to things far larger than we can touch. And that wonder, when held lightly, becomes calming rather than frightening. You begin to see the universe not as a series of warnings, but as a vast, quiet ocean carrying countless motions at once. Most of those motions will never affect us. Most of the cosmos will never even notice we exist. And strangely, there is comfort in that. Safety in scale. Peace in perspective. As your mind drifts, you might picture the final scene of this story. The sun settling after a flare, the nova light fading as it crosses new distances, the tectonic plates returning to their long, slow rhythms, and Atlas moving quietly back toward the dark that shaped it. Everything returning to its natural pace, everything resuming its ancient cycles. You are here, sheltered on a small blue world, listening to the echoes of distant events that come and go like passing waves. None of them ask anything of you. None of them change the ground beneath your feet tonight. You are safe within the quiet space between their motions. Good night, traveler. The universe is quiet tonight.